We have invented is a nanoporous material which has applications as a drug to treat a medical condition known as hyperkalemia, that is excess potassium in the blood. Now what we thought, perhaps it is possible to extend the realm of zeolites to metals other than aluminium. And we were particularly interested in transition metals because they could have properties different from the properties of aluminium silicates. We were expecting new properties from these materials, but essentially we just wanted to know whether it was possible to make materials with other metals and still keep silicon there and still keep porous structures. In the laboratory we cook the material very much like we cook something in a pressure vessel. So we mix a source of zirconium, a source of silicon, we make a soup, put it inside this temperature vessel, a pressure vessel, and we take it to the furnace, and typically after 2-3 days here comes out the new zirconium silicate with these very small channels hosting the potassium ions. 15 years or so late after we published the first structures of the zirconium silicates, the porous zirconium silicates, we got in touch with a company which was trying to use one of the materials we developed in a slightly different form and apply it as a drug to treat excess potassium in the blood, hyperkalemia, this medical condition. The new material was approved as a drug. Okay, and it's even in the hospitals now in Portugal. How the material works as a drug? You just have to imagine that these holes are reduced 1,000 million times, and we basically have the sort of structure we find in the zirconium silicate. So let's imagine this is a sodium ion, this lemon, and that this orange is potassium ion. And these are the channels of the nanoporous materials. What happens in the body is that these sodium ions are exchanged in the zirconium silicate by the potassium ions, the orange. And as you can see, the orange fits much better the available space. That means the interaction between the potassium ions and the atoms on the walls of these channels is much stronger. So the affinity of potassium ions is higher than the affinity of sodium ions towards these channels. And that's what ion exchange is, and that's what happens in your body.